Hi everyone. In this class we are going to see homomorphism and kernel. In the last class we have seen normal subgroup as well as quotient group. In this class we are going to see the definition of homomorphism, examples and kernel definition and some theorems. First we have to come with the definition of homomorphism. A mapping phi is from G into G bar is said to be a homomorphism if for every a comma b belongs to G, phi of AB is equal to phi of A into phi of B. Here phi is homomorphism, means we can separate phi of AB is equal to phi of A into phi of B. For homomorphism we are going to see the examples. The first example is phi of x is equal to E for every x belongs to G. Here this is the definition for every element belongs to G. Whatever element is belongs to G, that phi of that element is always E. So we have to show that this is homomorphism or not. This is trivially a homomorphism since phi of xy is equal to E. By our definition, phi of x is equal to E means phi of xy is also E. So E can be written as E into E. So for first E we have to write phi of x. The second E we have to write phi of y. So phi of x is equal to phi of x into phi of y means this phi is homomorphism. Similarly, phi of x is equal to x is also a homomorphism. The same thing you have to take phi of xy is equal to phi of x is equal to x is our definition. So phi of xy is equal to xy. By using our definition, phi of xy is equal to xy. For x you have to use phi of x, for y you have to use phi of y. So phi of xy is equal to phi of x into phi of y. So phi of x is equal to E is also a homomorphism. Phi of x is equal to x is also a homomorphism. Second example is very important 2-mark question. Let G be a group of integer under addition and let G bar is equal to G. For the integer x belongs to G, define phi is equal to, that is phi is from G to G bar by phi of x is equal to 2x. Here the group is under addition. So here the homomorphism means we have to show that phi of x plus y is equal to phi of x plus phi of y. So phi of x plus y is equal to, here our definition phi of x means 2 times of that element, 2 into x. So phi of x plus y means you have to write 2 times of that element, that is 2 times of x plus y. So 2x plus 2y. So 2x you have to write phi of x, 2y you have to write phi of y. So phi of x plus y is equal to phi of x plus phi of y. So this phi is homomorphism. Next we have to come with the third example. Let G be the group of positive real numbers under multiplication and G bar be the group of real numbers under addition. So here we are defining phi of G is phi is from G to G bar by phi of x is equal to log x to the base 10. Here listen, G be the group under multiplication, G bar is a group under addition. So here the homomorphism definition is phi of xy is equal to phi of x plus phi of y. So you have to read the statement carefully. G be the group of positive real numbers under multiplication and G bar be the group of all real numbers under addition. So we have to show that like this. So phi of x is equal to log x to the base 10. This is our definition. So you have to take phi of xy is equal to log xy to the base 10. So in the log you have multiplication means we can separate by addition. So log 10 to the log x to the base 10 plus log y to the base 10. So for the definition we have tried the first one is phi of x, the second one is phi of y. So phi of x is equal, phi of xy is equal to phi of x plus phi of y. So here this phi is homomorphism. Finally we have to come with the fourth example. Let G be a group of all real 2 by 2 matrices A, B, C, D such that AD minus BC is not equal to 0 under matrix multiplication. Let G bar be the group of all non-zero real numbers under multiplication. Define phi is from G to G bar by phi of AB, CD is equal to AD minus BC. Here is also phi is a homomorphism. The next we have to come with the theorem statement. The statement is, suppose G is a group, N is a normal subgroup of G, define the mapping phi is from G to G by N by phi of x is equal to Nx for every x belongs to G. Then phi is a homomorphism of G onto G by N. Here we have to show that the given definition phi is homomorphism of G onto G by N. In the statement itself they are given G is a group and N is a normal subgroup of G. They are also defined phi is from G to G by N by the definition phi of x is equal to Nx for every x belongs to G. So first we have to come with the proof phi is onto. The next is we have to show that phi is homomorphism. Phi is onto is a trivial because by the definition itself it will be satisfied. Phi of x is equal to Nx. Nx is the element of the form G by N. So here we have to show that phi is onto means for every x belongs to G by N is of the form x is equal to Ny. That is y is belongs to G. This Ny is equal to phi of y by given our statement. So x is equal to phi of y. So we have to prove that phi is a homomorphism. In the previous step it shows that phi is onto. So in the next step we have to show that phi is homomorphism. Phi is homomorphism means we have to show that phi of xy is equal to phi of x into phi of y. By definition, phi of x is equal to Nx is given in the statement itself. So phi of xy means N into xy. So the product of two right cosets of N in G is again a right coset of N in G. So here we have to use the statement. So Nxy is equal to Nx into Ny. So phi x into phi y. So which implies phi of xy is equal to phi of x into phi of y. Therefore, which implies phi is a homomorphism. So in this statement, we have to show that phi is a homomorphism of G onto G by N. So the next statement is, that is the next definition is a kernel. So this is very important 2-mark definition. Kernel means if phi is a homomorphism of G into G bar, the kernel of phi, that is we have to denote it by K phi, is defined by K phi is equal to x belongs to G, phi of x is equal to E bar, that E bar is equal to identity element of G bar. Here listen, phi is from G to G bar. X is belongs to G. We have to take the element from G means we have to define that phi of x, that mapping phi of x is equal to E bar. That E bar is the identity element of G bar. So identity element of G bar is denoted by E bar. So this is the definition of kernel. So next we have to come with the lemma. This lemma is very important 5-mark question. So statement is, if phi is a homomorphism of G into G bar, then phi of E is equal to E bar. That is the unit element of G bar. The second thing is phi of x inverse is equal to phi of x the whole inverse. For the second subdivision, we have to use the first subdivision. So simply they are asking the second subdivision alone means you have to use the first subdivision. So you should write the proof of first definition also, first subdivision also. Afterwards only you have to come with the second subdivision. So we have to come with the proof. The first one is we have to consider phi of x into E bar is equal to phi of x, because phi of x is as it is, E bar is the identity element of G bar. So you have to write identity element, you have to multiply it with anything means we get the same element. So phi of x into E bar is equal to phi of x. So instead of x we have to write xe. So phi xe. In the statement itself they are given phi is a homomorphism. So phi of xe can be written as phi of x into phi of E. So in the left hand side we have phi of x into E bar is equal to phi of x into phi of y. So here the phi of x will be cancelled, because by the left cancellation law you have to cancel phi of x is equal to. So we have to cancel phi of x means we get the result E bar is equal to phi of E. Now we have to come with the second subdivision. By our first subdivision we know that E bar is equal to phi of E. Instead of E, you have to write x into x inverse. Here we are going to use the phi is a homomorphism definition. So phi of x into phi of x inverse. In the right hand side we have phi of x, so that will be in the left hand side means phi of x the whole inverse. So e bar into phi of x the whole inverse is equal to phi of x inverse. So e bar is the identity element. In the next step we get simply phi of x the whole inverse is equal to phi of x inverse. So both the subdivisions are proved, hence the proof. The next will be, we have to come with the next theorem. The theorem statement is, if phi is a homomorphism of G into G bar with the kernel K, then K is a normal subgroup of G. Otherwise, the statement is like this. Let G and G bar be the two subgroups or groups if phi is from G to G bar is a homomorphism. Define the kernel of phi and prove that is normal subgroup of G. Both the statements will be equal. Suppose in the second statement will be your question, means you have to write the definition of kernel first. Find the, because in the statement define the kernel of phi and then prove that is a normal subgroup of G. So just you have to write the definition of kernel. Afterwards only you have to come with the proof. In the statement they are given phi is homomorphism and G bar with the groups with the kernel K. So we have to show that K is a normal subgroup of G. So first we have to prove that K is a subgroup of G. Afterwards we have to show that K is a normal subgroup. So first we have to prove that K is a subgroup of G. Already you know H is a subgroup of G means if and only if the closure property and inverse property will be satisfied. So you have to take closure property and inverse property. Here we have to show that K is a subgroup. So K is a subgroup means that is a kernel is a subgroup. Here we know the definition of kernel. K phi is equal to x belongs to G such that phi of x is equal to E bar. So phi of x is equal to E bar means we can say x is belongs to G or K. So the definition is phi of x is equal to E bar means we can say x is equal to x is belongs to K. So here we have to take the two element means we have to show that the product of this element will be belongs to K means we can say easily it will be closed. So xy is belongs to K means we have to show that phi of xy is equal to E bar. So here you have to listen here carefully because we have to show that kernel is a subgroup. So we have to take two elements x and y is belongs to K. So by our definition, K phi means x is belongs to G, that means x is belongs to K also. So phi of x is equal to E bar. The same statement here you have to use because this is the definition of kernel. So x comma y belongs to K means phi of x is equal to E bar. Similarly phi of y is also E bar, where E bar is the identity element of G bar. So x comma y belongs to K. We have to show that xy belongs to K. Xy belongs to K means we have to show that phi of xy is equal to E bar. So we have to take the left hand side phi of xy is equal to E bar, that is phi of xy is equal to phi of x into phi of y, because phi is homomorphism. This will be given in the statement itself. So phi of x into phi of y. Instead of phi of x we have to substitute E bar. Similarly instead of phi of y we have to substitute E bar. So E bar into E bar is equal to E bar. So phi of xy is equal to E bar means xy is belongs to K. So for every x comma y belongs to K, therefore K is closed. Therefore, the closure property is satisfied. The second thing is inverse property. So, inverse property means we have to show that x is belongs to K means we have then phi of x is equal to E bar. So, here we have to take x belongs to K means there exists x inverse is also belongs to K. So let x belongs to K, then phi of x is equal to E bar is our kernel definition. So by the previous theorem we have the second subdivision, phi of x inverse is equal to phi of x the whole inverse. So here phi of x is equal to E bar. So by the definition of kernel we have to write E bar the whole inverse. Identity element the whole inverse is again the identity element. So phi of x inverse is equal to E bar. So phi of x inverse is equal to E bar means surely we can say x inverse is belongs to K, that the kernel. So inverse property is also satisfied. So these two conditions are satisfied means we can say K is a subgroup of G. Now we have to prove that K is a normal subgroup of G. We know the definition of normal subgroup. Normal subgroup means G is belongs to G, N is belongs to N, G and G inverse is belongs to N. So here K is a normal subgroup. So K is a normal subgroup means we have to take small k is belongs to K, G inverse is belongs to K. So the K means that is belongs to in the kernel means we have to show that phi of G K G inverse is equal to E bar. So here you have to take phi of G K G inverse is equal to phi of G into phi of K into G inverse, since phi is homomorphism. Again the next step is also you have to use the same definition, phi is homomorphism. So this will be splitted as phi of G into phi of K into phi of G inverse. So phi of G into phi of K is a E bar, since K is the kernel. So K is belongs to K we are taken. So phi of K value will be E bar. So phi of G into E bar into phi of G bar. So E bar means identity element. So in the next step we get phi of G into phi of G bar. So G into G bar we have to write phi of G into G bar, since again we are using phi is a homomorphism definition. So G into G bar is equal to E. So phi of E is equal to E bar, because E is the identity element that will belongs to G. So phi of E is equal to E bar. So phi of G K G inverse is equal to E bar means we can say G K G inverse is belongs to K. So K is a normal subgroup of G, hence proved. Here you have to listen, K is a kernel. Kernel is said to be a normal subgroup means first you have to show that K is a subgroup, afterwards we have to come with the normal subgroup. Here the kernel definition is K phi is equal to X belongs to G, phi of K is equal to, that is phi of X is equal to E bar. So phi of X is equal to E bar means we can say X is belongs to K. So this definition only we are using to prove the subgroup as well as normal subgroup. So it will be clear means okay, otherwise you have to ask me, I will clear you. Thank you.